Hello, everyone. My name is Michael Lee, and I'm currently a master's student in the lab of Dr. Phidias Diamandis. Thank you so much for joining me in this talk today, as I'll be updating you on our lab's progress in the area of computational pathology, and as we've also recently published 2 new journal articles. There are a number of ways we can diagnose central nervous system tumors, and at the point of care, we have inspection and radiology imaging, such as CT and MRI scan. And the pros of this is that it is quick and very quick. It has a very quick turnaround. On the other side of the spectrum, we have molecular tests such as next generation sequencing. And while this is extremely precise and objective, the downside of this is that it may take up to weeks, and it could also be expensive as well. And where pathology lies is somewhere in the middle, as you can see in the middle here, with a routine hematoxylin and eosin stained slides, as well as immunohistochemistry tests that we can do. And this has the benefit of both cost efficiency as well as relatively quick turnaround time, while still remaining objective and quantitative. Now I'll discuss the modern neuropathology workflow, basically how pathologists work in their day-to-day life. And our starting point here is, again, hematoxylin and eosin, in short, H&E slide. In this case, we have a glioma here, and just from this H&E slide, pathologists would be able to tell that this is a glioma based on the morphology, essentially the shape, and different properties at the cellular level. But we would just know that it's glioma. So in the subsequent steps, we also want to find out what type of glioma it is, essentially subclassify the glioma into different subclasses. And to do that, we would need immunohistochemistry markers such as IDH1, R132H mutation, as well as ATRX, P53, and much more. We can order many tests. But just to simplify this figure, I've listed these 3 over here. And based on the combination of these 3 results, we would be able to come up with a working diagnosis. And in this case, it was an astrocytoma that's IDH mutated or IDH1 positive. And from then on, we can also order more molecular studies to get even better idea of what kind of cancer this is and what the progression would be like for the disease. So as I've mentioned, the advantages to this is that it has an excellent turnaround. It has low tissue requirements, and it is cost effective. But one of the downsides is that it requires many manual steps. So as I've mentioned, we have to look at the H&E slide at the tissue level, at the cellular level. We have to order a lot of these tests and also quantify them. And oftentimes it requires counting how many cells that are positive, how much percentage of the cells are positive for this particular marker, for example. So that's why currently computational pathology is on the rise, because the research question is essentially, could we develop an automated approach that mimics the modern pathology workflow? So my current master's project focuses on developing tools, different methods, whereby we essentially mimic the modern neuropathology workflow in 4 major steps. So the first step is histomorphologic classification. As I've alluded, this first step involves looking at different shapes and properties of the different brain tumor types. So meningiomas would have different shapes or appearance from gliomas, for example. And to do this, we use something called semantic segmentation, and which I'll describe in the subsequent slides of this presentation. The second step is biomarker quantification. And again, this requires quantifying biomarkers, which in this case, essentially these molecular markers that we would order after looking at the H&E stained whole slide images. The third step is integrating both the results from step 1 and step 2. And using what's called image registration, we would align the whole slide image of the H&E as well as the immunohistochemistry markers and analyze the tumor regions where we would quantify and find out more about different molecular markers. And the final step is kind of integrating everything together and then coming up with a diagnosis using decision trees. So I'll begin with the first step, which involves pattern recognition, histomorphologic classification, using something called semantic segmentation. And as you guys have probably heard by now, because it's all over the news and it's very trendy, we use something called neural networks. And the architecture behind it is based off of biological neural networks, as you can see in this image. And just like the biological neural network, where we have a cat, and then the image, based on the signal from the object, we would have different optic and nerve signals that go to higher order centers in the brain to ultimately come up with a classification that this is cat. The computational neural network also does it in a similar, very different, but in a similar fashion in that the architecture is similar. So you would also have different nodes or hidden layers where it would detect properties such as edges, shapes, lines, color, etc., to come up with an output. And all of this would be based on how you initially trained the neural network in the first place. So just like how we as children or adults even, we're constantly learning different things. We know what the difference between cat and dog is. It's hard to tell, but we just know it because they look different, right? Similarly, neural networks artificial neural network would also need to be trained what images of cat, what dogs look like to differentiate the two. And in computational pathology, and specifically for my project, we have developed a 16-class histomorphologic classifier where basically the computational, the classifier would be able to differentiate these 16 types of tissue. And so we have normal tissue such as white matter, gray matter, as well as non-lesional tissue that includes necrosis and blood, as well as, of course, our most important thing here, which is the lesional tissue, or essentially the different brain tumors. In this case, we have included meningioma, glioma, metastatic carcinoma, and schwannoma. And using tiles of these different images, different classes essentially, training images, we would be able to train a convolutional neural network, which takes these images, learns them from different labels such as glioblastoma, glioma, white matter, gray matter, the 16 classes I've shown here. And after the training is done, we would test it in order to verify that it's working as intended. And in this test image, it was a schwannoma. And once it went through, processed by the trained convolutional neural network, or CNN, it would come up with a probability-based score. And in this case, it was able to correctly identify the schwannoma as with 64% confidence. And what is great about this classifier is that here you have two different whole slide images of different H&E stained tissues. And it can come up with also a heat map to kind of tell you what the different regions of the tissue are. So in this case, you have necrosis in this sort of like pinkish, purplish color, and that represents around 54% of the area of this tissue. And of course, there's lesional tissue as well, 28% represented by black here. Similarly, in the bottom image, you can also see the breakdown of different classes from lesional tissue, etc., and a bit of blood here and there. And this is great because in the end, ultimately, the most important thing in our analysis is looking at the tumor. Oftentimes in the tissue that comes from the biopsy, it often contains artifacts and non-important regions that we're not too interested in, at least not in our analysis. And so this breakdown is important in the next major steps that I'll be discussing, and you'll find out more there. And as I've alluded previously, the four major tumors that we're looking at are meningioma, schwannoma, glioma, and secondary tumors or metastatic carcinomas. And in this pie chart, you can see sort of the general breakdown. And these four tumors essentially represent around 70 to 80% of all central nervous system adult tumors. And using these four tumors and using just a bit over 100 samples, whole slide images, we were able to come up with approximately 98% accuracy with a two that was misclassified being were schwannomas that were misclassified as meningioma. And these were sort of reasonable errors because the two whole slide images, they look very much like meningiomas, having spindle features and other properties that might be commonly mistaken for meningioma. So for a starting point, this was a very promising result. And also, these two could further be corrected if we were to use molecular markers, as I've suggested, such as SOX10 in this case. If it's SOX10 positive, you know that for sure it's schwannoma. But if it was negative, then all of a sudden, these two that were misclassified as meningioma, we won't be able to say for certain whether it was meningioma anymore. That's sort of the importance of molecular markers, not just for subclassification, but also just to ensure that the preliminary results from the histomorphologic semantic segmentation was indeed correct. Moving on to the next step then is the biomarker quantification. And in this case, we're using something called instance segmentation, which is essentially semantic segmentation using the convolutional neural network, but with the added addition of object detection. And we'll be using something called mask RCNN, where R stands for region. So on the top, you have the regular CNN, and this is just a tumor. Basically, the two different classes, you can represent them with different colors, brown here and pink. And what semantic segmentation does is it just kind of just generally looks at the different classes, where in this common image, you have 5 different people. That's how we would look at it. But using semantic segmentation, it would classify this thing as a whole and say that it's one person or one people, basically. But how can we ensure that we label each one of this person as a unique individual? And that's where mask RCNN comes in. And that's where why it's important for biomarker quantification is because we want to count each nucleus that are positive or negative for certain markers and basically count individual nuclei. And so using mask RCNN or instance segmentation, we're able to separate this image to the bottom right image and have each person labeled differently and have them as unique individual. And just to briefly describe how it works is that there are 2 stages. The first stage, we would have different region proposal network, my apologies, where basically it would draw different size regions, such as these rectangles over here. And within the regions, there would be different masks or different objects that would be identified and labeled. And in this case, you have these children with different colors. And so essentially, it's basically taking the CNN with different various regions of interest. And so we're able to identify each local images or local objects. And this is sort of the result from the mask RCNN that we have developed using annotated images of Ki67 and other nuclear molecular markers. And as you can see, the positive nuclei, which are brown in an immunohistochemistry stains, are depicted in red over here. And the negatives, which are blue, are depicted in blue in the heat map of this mask RCNN results. And we also have green for any miscellaneous non-nuclei artifacts, such as blood, red blood cells. And we wanted to then see whether the mask RCNN that we've developed to count and quantify the different nuclear stains would compare, how the performance of it would compare to that of pathologists. So we asked 3 different neuropathologists and took the pathologist average score of those 3 of different Ki67 images, have them quantify them, as well as have our AI tool, the mask RCNN tool, score these images. And when we drew this correlation plot, we were actually able to get a very, very high R value, meaning that the correlation between the AI score and the pathologist average score was very, very close. So the results were very similar. And in fact, when we compared the average R value between the AI and the individual pathologist and compared that to interpathologist R value score, we actually found that it was higher for the AI, meaning that the AI sort of classifies in a very balanced sort of way whereas different pathologists might have different criteria and might be in a sort of the extremes of the spectrum. So AI has sort of a consistent objective way of evaluating these scores, which makes sense because they would literally count every single nuclei that are positive, that are negative, and then divide that by the total number of nuclei. Yet there's still challenges that remain when we try and incorporate both what I've talked about with regards to the immunohistochemistry quantification, as well as the semantic segmentation with H&E stained whole slide images. Namely, if we try to align these images, it's not as easy as we think because oftentimes they're from different cuts of the same tissue. And so there might be horizontal translation, there might be 180-degree rotation. And this complicates things when we want to match different areas of this tumor to the corresponding area in the immunohistochemistry stain from the H&E, for example. And that's when where a computer vision tool that's not actually deep learning based called scale-invariant feature transform comes in. So this next major step is basically the interpretation part, where we're trying to sort of interpret and use something called image registration to combine sort of the results from the two images, or basically combine what we can analyze from the two different image pairs. And so, for example, we have this cathedral in this slide that was taken from different points. So ultimately, these two images depict the same object, but they are at different locations, different sizes, from different angles. And is there a way we can align this and ensure that this is the same object and different features or key points align to different to the same points in this object of the different image? And as you can see, if we use something called scale-invariant feature transform, or SIFT in short, we're able to essentially match and align the two images together. Similarly, in our computational workflow, we use SIFT to match different parts of the H&E and the IHC together. And this is just like a cartoon representing how this process works. And as you can see, we have different SIFT features that are aligned. So as you can see, these are basically the same regions, but are at different coordinates in the two different images. And so we're able to essentially match the two images and sort of combine the unify essentially the H&E and IHC workflow together. And so going back to these images again, when we had horizontal translation, we're still able to match and align the two images now with the added steps of converting them to grayscale and normalizing the pixel intensity, as you can see in the black and white over here. And even with 180-degree rotation, we're still able to match and align the two images despite the big differences in rotation. And just to sort of give an example of why this is important, and just to summarize everything I've talked about right now, on the top left, we have the H&E stained whole slide image of a glioma. And our first step, as I've mentioned, is semantic segmentation using the convolutional neural network, CNN, to come up with this heat map where brown denotes tumor and blue indicates necrosis and pink is blood. And the area that we're interested in is the brown area because that's a lesional, that's a tumor region. And as you can see, it only represents approximately 50% of the area, maybe even less. So, and on the top right, we have the immunohistochemistry stained whole slide image. And in this case, it's Ki67. That's the molecular marker. And when we combine this heat map result, as well as the IHC stain, we're able to come up with this. And with the addition of SIFT I talked about, basically aligning these two images together, using the heat map to know where the tumor region is, we're essentially able to focus our analysis in the tumor region only of the IHC stain, Ki67 over here, as denoted by the green highlight, so that we don't analyze the non-tumoral regions, such as over here on the bottom, on the top, on the bottom right. And this is important to get as highly accurate results when it comes to quantifying these images as possible. So we've essentially unified H&E and IC images together through SIFT, through our alignment tool. And just to end off this major step, we also looked into ways we can reduce total computational time, because we realized that sometimes our analysis takes too long, upwards 2 hours, because of the high demands of MassCAR CNN when it comes to looking at individual cells, each nuclei, 128 by 128 pixels across a gigabyte amount of size images. And so we wanted to find out then, could SIFT and random sampling of the tumor regions drastically reduce the time? And indeed, even when we used only 20 or 25% of the tumor region, we were still able to get similar Ki-67 quantification while being able to drastically reduce the total time here in the bottom right, or in the right side image, by quite a significant margin. So going from upwards over an hour on average, we were able to reduce it to less than 30-minute computational time on average. So finally, I also want to talk about an application of how we used sort of as a proof of concept of the tools that we've developed so far. As you can see here, this is the confusion matrix that I've shown earlier of the 4 major brain tumor classes. But according to the WHO classification of tumors of the central nervous system, we're able to subclassify gliomas as well as other tumors into different subclasses. And there are dozens, lots of subclasses that we can subclassify them. So our task is not complete with just classifying them into their major classes. And so we came up with this simplified version of this decision tree of glioma, whereby diffuse glioma could be further subclassified as IDH wild type or IDH mutant, as well as ATRX lost or ATRX retained, to have these 3 subclasses. And when we use this decision tree, as well as all the tools that we have developed so far, we were able to come up with an IHC-based glioma subclassification with 100% accuracy from approximately 34 samples that we've tested on. And just to demonstrate this, in the bottom images, I show an H&E stained whole slide image. And in the heat map version of it, after the semantic segmentation, the first major step of this analysis, and then using the immunohistochemistry, you can see that it's positive for IDH in the tumor region clearly, as tumor region is depicted by brown in the heat map. And when we only look at the tumor region, we're able to focus our analysis in these, essentially the 3 major blocks, which is represented here in the bottom right image, lesion-specific IDH assessment. And we're able to get over 90% quantification here. If we analyze the entire whole slide image, we probably would have gotten approximately 50 or 60%, which is much lower than it should be, because IDH positivity, ideally a lot of these immunohistochemistry stains should either be fully positive or fully negative. And so just to demonstrate this in another way, essentially we were able to increase the IDH1 positivity after using SIFT for the IDH1 positive whole slide images by a significant margin. And we were also able to do so for ATRX positivity for ATRX retained immunohistochemistry stained images. Just to wrap this presentation off, I'll briefly describe the last major step, which is sort of combining everything together and coming up with the ultimate integrated diagnosis. And to do this, we even intend to come up with a pathology-inspired report that is automatically generated. And as you can see in this prototype of our brain report, you can see the diagnosis, the results from the H&E, from the histomorphologic classification, the first major step, as well as the immunopositivity results from the second major step, as well as the decision from the decision trees, we're able to come up with an integrated diagnosis. And so this, we hope to be able to generate a report that has also other information, as well as that it's visually appealing as well, showing the different whole slide images, different heat maps, for example, different pie charts to show the different positivity, etc., and maybe perhaps even example tiles. And just to summarize everything I've talked about today, this workflow essentially summarizes a lot of the steps, especially the steps regarding SIFT and alignment and integrating different immunohistochemistry stains into our workflow, which was sort of the major breakthrough last year when when I was working on this project and in our manuscripts that we have recently submitted and been accepted. And so just to summarize everything again, in my current master's project, I was able to come up with 4 major steps that sort of mimic the modern neuropathology workflow, from histomorphologic classification to biomarker quantification, biomarker interpretation, and integrated diagnosis. And there are still some things left that I want to try and explore in my project, namely being able to grade the different brain tumors. So not only can we classify and subclassify brain tumors, but we can also grade them. For example, glioma could be grade 4, glioblastoma, which is a very aggressive malignant tumor type that reproduces itself very rapidly and has very high proliferation and aggressiveness. On the other hand, it could also be grade 2 that's less aggressive, much less aggressive. So depending on the grading, our prognosis could be very different. And to do that, to find out, we also need to look into additional features such as mitoses, microvascular proliferation, and necrosis, as you can see in these bottom 3 images. And so this will be my focus for the next few months until the end of my master's, so that we can essentially integrate this as part of our current workflow and be able to come up with an even more sophisticated, specific, precise diagnosis, as I've mentioned in our first slide, so that we can ultimately come up with better treatment plan, better care for the patients, and have this as sort of a companion for the pathologist in the future. I would like to thank everyone in the Diamandis lab for their continued support, specifically the AI team, Kevin, Madhu especially, who have worked on this tirelessly with me over the past year or so. And I would also like to thank my supervisor and committee members, Dr. Phidias Diamandis, Dr. Andrew Gao, and Dr. Ann Martel. And please consider subscribing to our YouTube channel if you haven't already, and if you have enjoyed this video. Thank you so much.